Okay, the subject of the lab this week is Newton's third law. And Newton's third law is the one that says, you've heard this before, for every action, there's an equal and opposite reaction. Let me finish writing this. That is not a super useful wording of this mathematically. So the way I want you to think about it is, if body 1 applies a force vector F to body 2, then body 2 applies a force vector negative F to body 1. And if you think about the meaning of, think about multiplying this vector F by a negative 1, that keeps the magnitude the same and just switches the direction. And that is a hard thing for people to wrap their heads around, because if you have a collision between two objects, so let's say that we have, a truck, and it collides with a little tiny car. It's hard to get used to the idea that they're each applying the same force to each other, because what happens in this collision is the truck keeps moving almost like it didn't notice there was a collision, and the car goes accelerating off. Well, the way that works is, if you draw a free body diagram of what's going on, the free body diagram of the truck there's a weight force, there's a normal force, and then there's the force, I'll call it F, that's applied to the truck by the car. And now let's go to a free body diagram of the car. What does that look like? Well, that also has a weight force, a normal force, and then there's a force here. And that force that's applied to the car by the truck is also F, just in the opposite direction. So how do you explain the fact that if those forces are the same, the truck keeps going like it was going before, and the car accelerates, with this huge acceleration? So why does the car accelerate more? And the answer to that is Newton's second law. Newton's second law says you take all the forces applied to an object, that's equal to the object's mass times its acceleration vector. Okay, well, what's the mass of the truck? It's really big, okay? And so if you rearrange this to calculate the acceleration, you get 1 over m times that F net. So let's say that horizontal component of F net is the same in both of these. We know it has to be. What's the acceleration for the truck? The m is very big for the truck, and so you're dividing this force by a very big number, and so you get a really small acceleration. Okay, for the car, that mass is a lot smaller. You're dividing by a smaller number, and that means the acceleration is a lot bigger. So it's not that the forces are different, it's that those forces, which have the same magnitude, affect those two bodies very differently because of their mass. And so in this lab, you're basically going to be doing the same things over and over again. You're going to be drawing some free body diagrams. You're going to be drawing a lot of those diagrams where you show the direction of the velocity, the parallel part of the velocity, the perpendicular part of the velocity, the perpendicular, part of the acceleration and parallel part of the acceleration that have to do with speeding up, slowing down for parallel, and then turning for perpendicular. And then it's also going to ask you, when these two objects are in contact with each other, what do we know about the forces acting on them? You know, are they the same size? The answer is those forces always have to be the same size, no matter what the collision looks like or the contact looks like. That's Newton's third law. That always has to be the case at every instant. But that does not mean that the acceleration magnitudes are the same. So if you have a very massive body and a very low mass body that are in contact with each other, the forces that they're applying to each other are the same, equal and opposite, but the accelerations produced by that contact are very different. The small body has a big acceleration, and the large body has a small acceleration. Okay, so for example, let's say that a cart comes rolling down this ramp and it picks up speed and crashes into this other cart at the bottom. Okay. This one has a big mass. This one has a small mass. When they're in contact, what do we know about the contact forces? Well, if you draw this free body diagram, you'd have a weight, you'd have a normal force, and you'd have some force F or R there. If you draw the free body diagram on the little one, you'd also have some weight, you'd also have some normal force, and then that contact force would be the same. Okay, and now these problems will ask you, okay, what do we know about the accelerations of these two objects? And the answer is the big body has a small acceleration in the direction of that contact force, because due to Newton's second law, we're dividing that contact force by a big mass to get the acceleration. And the small body has a large acceleration in the direction of its contact force. Okay, so that's the idea for this lab. Every question, think on every question about how this idea fit into the question, because it's going to come up over and over again. Email me if you have questions, or if you want to make an appointment to talk it over on Zoom or on the phone, email me and we'll choose a time. Okay, talk to you soon.